In this video, we are going to start with rules of differentiation, and we are going to focus on the power rule. You will find this on page 258 in the Namibian AS-Level Mathematics textbook, y equals mx+c to success. Derivatives or gradient function notation. This process of finding the gradient of a curve at any point is called differentiation. So basically the process of finding that formula that will give you the gradient at any point of a curve. The formula is called the derivative of y with respect to x and is denoted by dy by dx. So that's the way that you are indicating that it's the derivative. The formula is also called the gradient function. So in other words, we can say f prime x, read as f prime x, of the curve of y equals fx, because it can be used to find the gradient of the curve at any point. Okay, so very important. It's all about finding the gradient of the curve at any point. That formula, finding that formula. We will use three different notations. So the first two will be in the Leibniz notation. So if this is my equation, then dy by dx will be 2x, like we saw in the previous example. So that is indicating we were already differentiating this equation to find that 2x. Or we can write it, so sometimes they leave out the y on top, can you see? So it's d over dx, then they write that formula, x squared, so that's another way of writing, and then write the answer. Okay, so in this one, you can see the original formula or equation or part of that, that value of y again. If we differentiate x squared with respect to x, the result is 2x. Okay, that's a nice way of taking that part and describing it. And then the other one is the Lagrange notation. So this is, if we don't say y and we say fx equals x squared, then f prime x, so we make that little dash, is equal to 2x. Okay, so this is actually meaning exactly the same. It's just two different notations. Now we're going to start with the rules of differentiation. The derivative tells us the formula for the gradient of a function at any point. So that formula can find the gradient at any point. Let's look at some rules we can follow to find many derivatives. And we're going to start in this video by the power function, differentiation of power functions. We know now from the previous video, and I want to go back, and because out of this I want to show you how we come to the formula. In the previous video, if you can recall, we said, okay, we were taking first principles. We take the equation y equals x squared. Do you see? Y equals x squared. Then we used first principles and we got that 2x. From x squared, we got 2x. So basically, what did we do? So I'm going to take you back. Okay. So if you look, that was 2. And if you see nothing there was standing actually a 1. So basically, we took that exponent, that index, and we multiplied with the coefficient to get that 2. And then basically, if you look, the coefficient is 1 less. So 2 minus 1, that will be 1. Okay, and that's actually the rule. So if we test it in this one, what's the coefficient? 1. If we take that index, okay, and we multiply it by the coefficient, we get 3, and then we subtract and we get that 2. So, therefore, the general rule for differentiating power functions is, okay, there it is. This is in that notation that we wrote it. So, for any real power of n, not only for positive values of n. So, that n value can be negative. It can even be a fraction. Okay, so what we do is we subtract 1 from the index. But before we do that, we take the index and we multiply it by the coefficient. Okay, So if that is 4 and that is 1, so we say first the index, multiply the coefficient to get that 4, and then subtract 1 from the index. Right, let's just move it up a little bit to see. How do we remember the power rule? Like this. Multiply the index, you see that's the index, that little small number on top, the exponent. Multiply the index by the coefficient, so the number in front of the variable. And then after that, subtract 1 from the index, and then we subtract 1. So we first multiply and then we subtract 1. Okay, let's look at a few examples. Okay, so this is now, this is all my equations. So I'm going to use this because I don't see y equals or fx equals, then it's good to just go to this notation. D over dx, and there I write this. So remember, take that 6, and I even want to make it a little bit bigger. You can see better. Okay, I think this is going to be better. Okay, so 6 multiply 1 is 6 and subtract 1 there. So multiply by the power 6 and then subtract 1 from the power. Okay, if you look at this one, we do exactly the same. There's a 1, so I multiply that 3 over 2 or 1.5. So I get 3 over 2 and then subtract 1. Now, usually because it's fractions, it's so easy to make mistakes. So to write the index like this will help, especially in the beginning. Say 3 over 2, but because minus 1, so if that denominator is 2, subtract 2 over 2. If the denominator was 4, subtract 4 over 4. If the denominator was 5, subtract 5 over 5, but I'll show it in another example again. Okay, for now it's 2, so I subtract 2 over 2. And if I'm going, then it's easy. Then you can say, oh, it's a half. And now it's not necessary, but you can take that from that exponent, that fraction, you can take it back to the root to search form. And that will be square root x. Okay. Now, in this case, okay, now if you look at this example, there was not a y, but now I see a y. So now it will be better to just say dy by dx. Okay, so basically I'm just going to do, but before we do that, if you see that this variable is inside a root, first take it to an exponent. Now can you still remember how we did that? So if there's a 1, oh, the color is not good, let's take another color. If there's a 1 and if there's nothing standing with the root, then there's a 2. So always the 1 comes on top and the 2 is the denominator at the bottom. So first convert from root notation to index notation. So I did not differentiate. Now I'm going to differentiate. So dy by dx, and now take the exponent, the index, multiplied by the coefficient, which is 1, and I get a half, and then subtract. So subtract 2 over 2. That's basically what I did there. Okay. And then again, subtract 2 over 2. And then I get negative a half. But I don't want it negative. And remember, if it stands there, it actually means it stands on top. Okay. Now I can bring it down to the bottom. Okay, bring it down to the bottom. And now I can take it back to the root form again. Okay, to root notation. So it's either this or this. And then the next one, oh, there's just a constant. But I want to show you, if there's just a constant, there's actually standing x to the power of 0. So do exactly the same. 0 times 2, oh, what will that be? 0. And if I subtract, say 0 minus 1, I'm going to get, in this case, so 2 times 0, although I'm going to get x to the power negative 1, but as soon as I multiply with that 0, everything is just going to become 0. So this is very, very important. When you differentiate a constant, the answer is always 0. Okay, because it's from that 0 that you multiply, and as soon as you multiply something by 0, then everything will become 0. Okay, very important to remember that. And then the final one I'm going to show you here. Okay, so if I get one like this, if the variable is in the denominator, do you see? First, take it to the numerator. Take it to the top. Now, as soon as I take it to the top, if this exponent was 1, then it will become -1. And now I will go into differentiation. So now I will say, okay, I take the index, I multiply it with the coefficient, so I get -1, and -1 subtract another -1 will be -2. And then I don't want to leave it like this. I want to have it positive. So I'm taking it from the numerator to the denominator. Leave that negative in front. Don't throw it away. I just want to say something here that's important. Answers to derivatives can be given either in search form, that's I'll show you, can be either like this, that's search form, or in fractional index form, or like that. Negative indices are allowed in the numerator, but not in the denominator. Okay, so it can be in the numerator, but as long as it's not in the denominator. Do you see? So there it's actually also correct, but not in the denominator, as this implied double fractions. Okay, I want you to stop the video and I want you to do the following numbers. After you are finished, you can continue the video as soon as you are done. Just let's mark the examples. There's a few coming. But I only want you to do number A, C, E, F, and K. That's the ones I will explain on this video. Okay, let's start. I'm just going to make it smaller to have more space to write. And very, very important, as soon as you start with differentiation, make sure that you are writing the things correctly. Okay, so I'm going to focus on that and I'm going to emphasize a few things. So we are at try now 1. And we are going to start with number A. And that was given like this, x to the power of 8. Now, usually, if they don't say y equals or fx equals, then usually I'm going to go for this notation. Do you see? So I will say, okay, d over dx, and then I will put in bracket that x to the power of 8. And now I will write the answer. So that's implying I'm busy going to differentiate this now. So I take this, unclear. The coefficient is 1, so I multiply it by 8. And then I just subtract 1. And that's that. 8 minus 1, 7. That will be my answer. Let's go to the next one. Number C. So this will be y equals, and this is a root, and this is x to the power of 3. Now, remember what I said? We cannot differentiate if it's in a root. So, also, don't indicate. There I indicate I'm busy differentiating. So, don't indicate. You are not differentiating now. You are just getting it ready to differentiate. So, I'm going to, remember there's a 2. So, it will be x, and it will be 3 over 2. Okay, that's basically what it's going to be. Now I'm going to start with my differentiation. So now, because there's a y, the easiest one will now be to say dy by dx. So this indicates this formula that's following now is differentiated. And that can give me the gradient of a curve at any point. Okay, and that we will come to in this chapter. So in this case, again, it's 1. So if I multiply, so it's going to be 3 over 2, because it's just multiply 1, and x. Now, again, I'm going to do it little. So I like to say 3 over 2, just in the beginning, just to help you. So because it's the denominator is 2, I subtract 2 over 2, and that is going to give me 3 over 2 x, and that is going to be a half. I can leave it like that, or I can write it as, I just want to continue that one, 3 over 2 square root x. I'm taking it back to root notation. Okay, let's do the next one, number E. So if I look at number E, oh, it's a nice one, because it's a constant. And then when you differentiate a constant, the answer is always 0. But write it now. Don't say equals 0. Don't do that. That's not correct. Indicate dy, this is the differentiated formula, over dx is equal to 0. Do it like that. Okay. I'm going to go to the next one, number F. So I'm going to just clean, otherwise my space is not enough. Okay. And now I'm going to just go to, let's just test these colors. This time I see yellow. Okay. F. So this is going to be y equals, and this is going to be, this is a bit unclear, so I'm going to write it for you down. Hope you saw it. It was x to the power negative 4 over 5. Okay, now in this case, I'm going to start. So because it's y, I like to go for this notation, dy by dx equals, now there's a 1, so if I multiply negative 4 over 5, but look now, I want to show you nicely. So I'm subtracting 1, but write the 1 like this. This is what I'm implying every time. Say minus 5 over 5, because the denominator is 5. Then you don't make unnecessary, especially in the beginning, then you don't make unnecessary mistakes. And that is going to give me the negative 9 over 5. Okay, now I don't want it negative, I prefer positive. But now it's almost like, and I can just show you here, it's like there's a multiply and this is over 1. So actually this is on top. Now if I want to bring it down, it will end up with the 5. So in this case, bringing it down, it's going to be x to get it positive over 5. Okay, and I can even go further and put it in a root. And then the one on top is inside, and this is the one at the bottom. And that will be my final answer. Okay, let's go for number K. It's very important that you practice these rules a few times, even if you do the same sums a few times, before you start with the application of the rules. Because there's quite a few. This is just the beginning. Okay, this one, here we comes to the other notation now. Okay, this is very important. This is a nice one, very nice one to show a few things. So the first thing, we don't like the root. Get it out of the root. I'm not differentiating. I'm just getting this ready for differentiation. So don't go with f prime x. No, just go x 2 over 3. That is top, bottom. You cannot work with it if it's in the denominator, the variable. The variable must be in the numerator. So take it, x, and now if it's a positive, if it moves up, it becomes a negative. Okay. And now, for the first time, my formula is ready to start differentiating. Okay, you see, 2 over 3. So now I'm going to say f prime x. Now I'm differentiating. So I multiply with the one in front. And now, just to help, remember I subtract always 1, but again, I want to do it like this. Do you see? The denominator is 3, so I subtract 3 over 3, just to help me, not make unnecessary mistakes. And the signs are the same, so it's negative 5 over 3. Okay, and now I can get it back. So this is now actually on top. So if I want to change the sign, I must take this to the bottom. You see, I'm taking it to the bottom. And now I can put it back in the root, which will give me negative. Don't throw the negative away. There's my root. There's my x. There's my 5. And it will be a cube root. There's my 3. And you have to indicate that. Okay, that was the basic rules, a few basic rules. We will continue with the rules in the next video.